Okay, counting using one-to-one correspondence. So, counting with one-to-one correspondence. Sometimes called bijection. So this one-to-one correspondence we're talking about is called bijection. Okay, and it's a little bit more sophisticated than build-up counting and sum and product rule, because sometimes there's a little bit of creativity involved in finding such one-to-one correspondences, and we'll see some examples. Okay, but when it works, boy, it is very powerful and very beautiful. Okay, but when in doubt, you should fall back on build-up counting, because that usually works. It's the workman-like approach. Okay, this is the more creative approach, but very powerful. Okay, so imagine I have a set A, and I've counted the set A, and this set A has 5 elements. Now I have a set B. Okay, and what I've managed to do in this set is I've managed to set up a one-to-one correspondence between the elements of A and the elements of B. So how would such a correspondence look? So one-to-one means that every element of A is uniquely matched with an element of B and vice versa. Okay? So this might look something like this. Okay, so there are elements of B, and every element of A has a correspondence with an element of B and vice versa. Okay? Such a relationship that associates all the elements of A and B into pairs is called a bijection. Okay, and sometimes we say that A maps both injectively and surjectively onto B. But the most important thing is that when you have set up this one-to-one correspondence, we've counted the elements of A, we haven't counted the elements of B. We know that B must have 5 elements, as in this example. So if you have a bijection, if you have this one-to-one correspondence between A and B, and I'll write that as A has a bijection to B. And bijection is just the sophisticated mathematical word for this type of one-to-one correspondence. Then the size of A equals the size of B. Okay, that's the fundamental idea behind bijection. So it's like this. In the audience, in the auditorium, there are some number of seats. I don't know how many seats there are. But if every student has a seat, so students are matched with seats, and every seat is occupied, so seats have a corresponding student, then I know that the number of seats equals the number of students. So if I know that there are 350 students in the class, I know that there are 350 seats in the auditorium. Now, if some seats are empty, then I know there are more seats. If some students don't have a seat, then I know there are more students. Okay? But when I have the one-to-one correspondence, I know it's equality. And that's what the bijection or the one-to-one correspondence establishes. Okay? So, let's do some examples of how this can be useful. Basically what it says is, if I know how many elements are in A, I don't need to count B if I have a bijection. And so that can save us time and effort if we have standard sets that we've counted, and then we get bijections to the other complex sets that we'd like to count. So let's start with party planning committees. So you have 10 students. Okay. Remember, when you have 10 students, the number of committees is equal to 2 to the 10. And how did we get that? Because the committees are uniquely identified by a binary sequence S1, S2, up to S10. That was a bijection from the committees to the sequences S1 to S10. Bijection means one-to-one correspondence. Every committee corresponds to a sequence like this, and every sequence like this corresponds to a committee. And how did they correspond? Well, the ones in the sequence correspond to to the students that are picked for the committee. Okay. So, 1 means picked, and 0 means not picked. Okay? And so every binary sequence of length 10 gave us a committee, and every committee corresponds to such a binary sequence. So that establishes the bijection or the one-to-one correspondence. And so we know that the number of such committees is exactly the number of such sequences, which is 2 to the 10. We saw that before. Now let's add a twist. Supposing that I want my committee to have exactly 4 members. Number of committees with exactly 4 members. It means that I need my sequence S1, S2 up to S10 to have exactly 4 ones. This means S1 up to S10 has exactly 4 ones. Okay, so this is a binary sequence in which 4 students are picked, i.e. it has exactly 4 ones. But the number of binary sequences of length 10 with exactly 4 ones, we know what it is. It's 10 choose 4. Okay. Now, we could compute that with Pascal's triangle and the build-up method, but for the moment, I don't want to illustrate that we can compute this. What I want to illustrate is that we were interested in the number of committees with exactly 4 members, and using this one-to-one correspondence that a committee with exactly 4 members corresponds exactly to a binary sequence with 4 ones. Okay. I know that the number of such committees is exactly equal to the number of such sequences, and that's equal to this binomial coefficient that we defined earlier, 10, 4. Okay. But now let's see what 10, 4 is. It's the number of ways to choose 4 members from a set of 10. So the number of 10-bit sequences with 4 ones is also equal to the number of ways to choose 4 elements from 10. In this case, we're choosing 4 students from 10. And that's why sometimes this is called 10 choose 4. The binomial coefficient 10, 4 is sometimes called 10 choose 4 for exactly this reason. That there's a one-to-one correspondence between binary sequences with 4 ones, which was the definition of 10, 4, and the number of ways to choose 4 members from a set of size 10. 4 elements from a set of size 10. We don't know a formula for this guy yet, but at least we've established, that, both of these things have the same number. Okay? And that's the value of bijection one-to-one correspondence. Okay, let's do another example. Goodybags. Remember, we defined this guy Q of N and K. So let's compute Q of 3 and 3, which is, the number of Goodybags with 3 candies when there are 3 colors of candies. Okay. Now let me think about how would I tell you what's in my goodie bag. Let's say I've created such a goodie bag with 3 candies. How would I tell you what's in there? So I have 3 colors. So let's call this color 1. Let's call this color 2. Let's call this color 3. Okay. And one way to tell you what's in this goodie bag is to tell you, how many candies do you have of color 1? Let's say you have 2. How many candies do you have of color 2? Let's say you have none. Okay. And how many candies do you have of color 3? So in this case, you have 1 because there are 3 candies in total. Okay. Now I need a way to identify that, there are 2 candies of color 1 and that's the end of color 1. So I can put a delimiter here. Okay. And then now I'm going to tell you how many candies of color 2. There are none. So I'll put another delimiter here. Okay. And then how many candies are there of color 3? 1. Okay. And so if I showed you the following, 0, candy, delimiter, candy. Okay. That means that there's 2 of color 1, 1 of 0 of color 2, and 1 of color 3. Okay. So let me give you another example. Practice. Tell me what goodie bag this corresponds to. 0, candy. Pause for 1, 2, 3 seconds. And if you're coming back and you said 3 of color 1, 2 of color 2, 3 of color 3, that's correct. But this delimiter is telling you when does candy 1 end, color 1 end, and when does color 2 start. And when does color 2 end, and when does, and then color 3. Okay? Now, what is this goodie bag? So another goodie bag with 3 candies. What is that goodie bag? Okay, 0 of color 1, 0 of color 2, and 3 of color 3. Okay. And what is this goodie bag? 1 of color 1, 1 of color 2, 1 of color 3. Okay, now let's look carefully at this guy here. And you will see that, this looks very similar to a binary sequence with 2 ones. A binary sequence with 2 ones. A binary sequence with 2 ones. In fact, any binary sequence with 2 ones and has length 5 will give us a goodie bag with 3 candies that are exploring my 3 colors. So let's take a random binary sequence with 2 ones. 0, 0, 1, 0, 1, 0. Oh, 0, 0, 0, 1, 0, 0, 1, 0, 1. Okay, so this is a binary sequence of length 5 with 2 ones, two candies of color 1, 1 of color 2, 0 of color 3. Any binary sequence of length 5 with exactly 2 ones has a 1-to-1 correspondence with goodie bags that have 3 candies and where the number of colors is 3. So what we have just established is that Q of 3 is exactly equal to 5, 2. The binary number of binary sequences of length 5 with exactly 2 ones. Let us see if we can now go directly and compute Q of nk. Okay, the number of goodie bags when you have n candies with k colors. Q of nk. Well, I have k colors, so I have color 1, color 2, color 3, up to color k. I'm going to need a delimiter, i.e. a 1, to separate each of these different candies. So since I have k colors, I'm going to need k minus 1 delimiters. K minus 1 delimiters, i.e. 1s. Okay. Now I'm going to put my candies into each of these boxes. Okay, and a candy corresponds to a 0. Okay, and I need to have n of these zeros. So the total length of this binary sequence is n plus k minus 1. So the total length of this binary sequence is n plus k minus 1. And how many 1s does it have? K minus 1. So that establishes the correspondence that any binary sequence with k minus 1 ones that is of length n plus k minus 1 corresponds to a goodie bag with n candies that uses k colors. So these two numbers must be the same. Wow. Okay. So the number of goodie bags when you have n candies and k colors is exactly equal to the number of binary sequences of length n plus k minus 1 which have exactly k minus 1 ones. Now you can go and check Pascal's triangle for this guy and the build-up counting table that we built for this guy and verify this equality. You'll be stunned. Wow. Goodie bags, binary sequences, Pascal's triangle, they're all related. Okay, so let's erase. I'll give you a couple of problems. Okay, and then we'll talk about permutations and combinations. Okay, so let's think about this problem. You have a chessboard, 8x8 chessboard. And on this chessboard, I place a king somewhere and a queen. Okay, now you might think about, there's the standard chess way to identify squares in the chessboard. You have letters A, B, C, D, E, F, G, H. 1, 2, 3, 4, 5, 6, 7, 8. And you can think of this, the position of the king could be given by D3. So D3, that's the position of the king. And the position of the queen is F5. F5. And we might ask, how many king-queen positions, pairs, how many positions are there for this king-queen pair? The queen cannot be on the same spot as the king. So, build-up counting says the position for the king, there are 64 choices. Okay, product rule says that there are 64 choices here, and once you pick the king's position, there are 63 choices for the queen. So 63. So you have 64 times 63. Okay. Now, the interesting twist on this problem is, supposing instead that I replace the king and the queen by two black castles, or rooks, as I used to call them. Rook, rook. So two black rooks. Okay, now you might think, well, what's the difference? Why isn't it? So we're assuming that the two black rooks are identical in every possible way. So you might think, well, the first rook can be placed in 64 ways, and then the second rook somewhere else. So there are 63 other squares. What's the difference? Isn't this the number of positions, distinct positions for the rook-rook pair? And it turns out that we have overcounted the rook-rook pairs, and this is related to a concept called multiplicity when we try to establish a one-to-one correspondence. So, it turns out that there are exactly half as many identical rook-rook positions as king-queen positions. Okay. And you need to sit down and sort of try to convince yourself, yes, that's true. Okay. Why? Because in the king-queen case, the king here, and the queen here is a different position from the queen here and the king here. Whereas in the rook-rook case, when you flip the positions of these two rooks, it's the same position. Okay, so there are twice as many king-queen positions as there are rook-rook positions. That's related to this concept called multiplicity in counting. And when you establish correspondences, you must make sure that there's a one-to-one correspondence. So read about it in the text in the chapter. Okay, we're going to move on to permutations and combinations. So let's erase.